So we're moving on in Gen Chem 2 lab to do titrations. So we're going to spend a couple of labs here where we do titrations. So at the beginning of this first titration lab, I'm going to go into some theory both about what a titration is and then also the kinds of information we can use a titration to tell us, and then specifically what it relates to in this experiment, which is a strong acid, strong base titration. All right, so a titration, introducing you to some of the terminology, we often have something called a titrant, which we are going to keep in our burettes. Now, we've been using burettes for several labs already, so you should know how to use those pretty well. And then we're going to have an analyte, and that's usually going to be in a beaker or it may be in an Erlenmeyer flask. But what's at the core of a titration is chemistry happens between a titrant and an analyte. So there's a chemical reaction that's generally happening. Now, what do we know in a titration? Well, in general, we are going to have something that we know the concentration of with a high degree of accuracy, and that's going to be our standardized solution. Usually that's what you have in your burette, and we're going to be adding a known volume of that titrant to reach an end point of a reaction with our analyte. So our analyte is usually something that we're going to add a known volume of our analyte, but we don't know the concentration of our analyte. Okay, so many of things in chemistry, we're going to have something that we know and something that we don't know. So think back to some of the other labs that we've done, particularly 2 labs where we've used our spectrophotometer. In those, we created what we call a standard curve. We had known concentrations of something that we had a linear relationship with Beer's law to create a standard curve. And the slope of that standard curve could be used to determine the concentration of that colored species in an unknown solution. So a lot of what we do in chemistry has information that we know, and we use it to determine information that we don't know. So in this case, we're going to have chemistry happening between the titrant and the analyte for a titration. Okay, we're going to have, again, a known concentration and volume of our titrant, which means we can determine the number of moles of titrant that have reacted. Remember, concentration is moles per liter. And if we multiply that by the volume that we use in liters, we can get the number of moles. So we will be able to very accurately know the number of moles of titrant that we use. And via a balanced chemical equation, we can determine the moles of analyte that we react with. Now, again, we don't know the concentration of the unknown, but we are going to know with a high degree of accuracy the volume of analyte that we're going to use. And since molarity is a ratio between moles and volume, since we just figured out the number of moles and we already knew the volume that we had, we can determine molarity. So just a quick thing to highlight here. We know the volume of our titrant with a high degree of accuracy because we're using a burette. We know the concentration of our titrant with a high degree of accuracy because we're going to use what's called a standardized solution. We already did for you another experiment to very accurately determine the concentration of our titrant. So it's called a standardized solution. We are going to know this accuracy to 4 significant digits beyond the decimal point there. Well, how are we going to know with a high degree of accuracy the volume of our analyte? We're going to use a pipette for that. Remember the pipettes that we have with those rubber bulbs? We're going to use those to accurately know the volume. So all of these pieces, we know 3 pieces here with a high degree of accuracy is going to allow us to have a fairly high degree of accuracy that we will be able to determine our unknown concentration. So that's in general how a titration works. So what's going to be different in these different labs that we do that involve titrations are the chemistry happening between the analyte and the titrant. So the last piece to know here is, well, how do I know that I've actually had the same number of moles of titrant react with the same number of moles of analyte? We call this stoichiometric equivalence. I've reached what's called the equivalence point. So how do I know I'm there? How do I know that I've reached this equal molar amount? Well, what actually has to happen is we need to have a little bit of excess titrant that we're going to add, and we're going to have an indicator in our solution that will turn color when we have just the slightest excess of our titrant. Okay, so we're going to talk about what that is in just a minute here. But let's see first. So This is the generalized way to think about a titration. What are we specifically doing with this strong acid, strong base titration? Well, again, we're doing a titration. We're going to be using sodium hydroxide and hydrochloric acid. Strong base, strong acid, right? So we're going to be using sodium hydroxide as our titrant. So that's going to be the solution that we know with a high degree of accuracy because it was standardized. So this number is just a number from previous years. It's not necessarily going to be the number for your lab solution. And we're going to be titrating this sodium hydroxide into a specific volume of HCl that we don't know the concentration of. So we're going to have a known concentration of sodium hydroxide. We're going to add a known volume that we'll measure with our burette. We're going to be adding that to a known volume of HCl that we measure with a pipette, and we're going to be able to do those calculations then to determine the molarity of that solution. So let's talk a little bit about that question of, well, how do I know that I've reached this point where the moles of sodium hydroxide will equal the moles of HCl? Well, we're going to be able to use an indicator called phenolphthalein that'll tell us when we've reached that. So when phenolphthalein is in an acidic solution, it's going to be colorless. So when the moles of HCl outnumber the moles of, and it shouldn't say sodium chloride there, that should say sodium hydroxide. Let me fix that real quick. We've got sodium hydroxide there. When the moles of sodium hydroxide is going to be less than the moles of hydrochloric acid, we're going to have a colorless solution. Even when we have the moles of sodium hydroxide that are equal to the moles of HCl, that's still going to be a colorless solution. So again, what's happening with our titration reaction here is we are dripping in hydrochloric acid or our sodium hydroxide into our hydrochloric acid, and this solution is going to be colorless. You'll actually see when this sodium hydroxide first drops in, you'll see little splotches of pink that are in here that go away as we have this neutralization reaction proceed. And as we get more towards this stoichiometric equivalence point, what's going to begin to happen is that pink color will stick around for longer and longer, until eventually we get to a point here where we're going to have our sodium hydroxide concentration will be in excess. And at that point, our solution will turn and at that point stay pink. So what we're looking for here, it would be ideal if we could see when we got to this point, this stoichiometric equivalence point. But we can't see that point. We want to get just past that point where it's just the slightest shade of pink. So I'm going to show you a couple of actual pictures here for what you're going to see. I like to give titration awards for, whoever has the lightest shade of pink color, right? So we're going to be monitoring this. So let me give you a little bit of chemistry with how phenolphthalein works. Phenolphthalein is actually what we call a pH indicator. It's a dye that changes color depending on its protonation state. Our last lab, our equilibrium lab that we had, that was actually a pH indicator too. Remember, it turned yellowish if it was an acidic solution. It turned bluish if it was in basic solution. And when we were kind of in between and had both colors, then we had green. That was a pH indicator as well. This one's a little bit simpler because it's a binary sort of indicator. It's either on or off, pink or colorless. So here's how the chemistry happens. When this dye molecule is in its acidic form, it's protonated. Okay, when it's in acidic solution, it's going to be colorless. But as we're adding in hydroxide, what's going to happen is we're going to be removing that proton. And remember, that hydroxide that we're going to be adding is going to be reacting with our HCl. It's only when this hydroxide is in excess, when there's no more hydrochloric acid there, that we start seeing this pink color. So again, we've got a colorless solution here that's eventually going to become pink. So let me show you some actual pictures here. You do not want to have a pink that looks like this. You've added way too much excess sodium hydroxide there. This is what it looks like again when it's colorless. These are just a couple of pictures from last year's titration. This is still a little bit too pink. This one was one of our titration winners. You want to get to be as close to colorless as possible, but still seeing a shade of pink. So that's what you're kind of working for, is to kind of have that slight shade of pink. All right, so let's talk just a little bit about the calculations that you're going to have to do. We'll have another video that Dr. Brown will do that'll walk through some more of the actual calculations. But in theory, right, we've got this chemical reaction where we have a certain volume of sodium hydroxide that we added from our burette. We're going to know that exact volume because that's the exact volume that we need to get to the slightest pink color, right? So we're going to know that by measuring the difference between our starting burette reading and our ending burette reading. We're going to multiply that by the molarity of the sodium hydroxide, right? That molarity is going to be the concentration that we have of that standardized solution. So we know that with high degree of accuracy. That's going to get us to the number of moles of sodium hydroxide that we added. Now, our balanced chemical equation will allow us to change who we're talking about, and we'll get the number of moles of HCl that reacted. So that is one piece of our information that we need to calculate the molarity of this hydrochloric acid solution. We then need to divide it by the volume, and I shouldn't have, apologies for this, this should be the liters of HCl that we have, how much we added by our pipette. So we're going to be adding about 25 milliliters using a volumetric pipette. So we're going to know that volume exactly. And then when we take the division of both of these, the number of moles of HCl divided by the liters of HCl, that will give us the molarity of our HCl solution, and that is our unknown. So we'll see how many times you're able to repeat this titration in lab, because in lab we always like to repeat measurements because that gives us precision and more confidence in the accuracy of our value. But that's how we're going to go through and do this strong acid, strong base titration.